And ultimately, the first part of this section starts out with just some more rules here. And all the rules that are presented here in the first part of this are the same rules that we had in the chart in the previous section. They're just ultimately written in essentially the chain rule form, if you will. So instead of x to the n as our integrand, it's u to the n. Okay? And keep in mind that the rules are exactly the same. All right? So what it boils down to is that, as we showed yesterday, if we extend our work here in terms of trying to figure out how we deal with this chain rule situation, so the example, if we have x minus 4 to the fourth power, let's say, we'll use as our example, and we want to find the answer to this. Well, we have two choices essentially at this point. Our first choice here is we could expand that, and since it's to the fourth power, that wouldn't take terribly long, and we just have a fourth degree polynomial that we could go term by term and find the antiderivative. True? Okay, however, we don't have to do that because we have another method. If we could write this as u to the fourth, okay, then we would just have a straight u to the fifth over 5 antiderivative. True? So the question is, how do we do that? What do the mechanics look like for that? Well, ultimately, we would do that. If we were to be able to do that, we'd have to substitute that x minus 4 and get it out of there. Okay? The problem is, we can't write an equation that looks like this, or an integral that looks like u to the fourth dx. That wouldn't make sense. Okay? The answer to u to the fourth dx is not u to the fifth over 5. If it was u to the x, u to the fifth du, then it would be. Okay. So the question is, how do we get that dx out of there? Well, ultimately there's a relationship I showed you yesterday between du and dx generally. And ultimately the derivative here is just going to be 1 dx. So in this particular case, this is the simplest sort where du and dx are equal. Okay? Because ultimately what is du? It is the derivative of u, okay? The differential u I should say, which equals the derivative of the argument times dx. Which ultimately stems from du dx equals 1 here in this case. So, with that said, if I know that du and dx are equal, then wouldn't I just be able to write du instead of dx? And once that's accomplished, now I can go ahead and do my antiderivative. So my answer here would be u to the fifth plus 5, I don't know where that came from. U to the fifth over 5 plus c. And therefore my final answer would be substituting the x stuff back in there, so it would be x minus 4 to the fifth over 5 plus c. Right. And that would do it. Alright. So ultimately we're still using the same rule, we're still using the power rule here, but ultimately we need to get it into the form where it's in the form u to the fourth instead of something else to the fourth. And ultimately, if we have anything that's raised to a power like that, we can use that same exact technique each time. Okay? It's going to be a little more difficult with some of them that we're going to do here because ultimately the derivative here was just 1, which makes it a fairly simple chain rule problem here. All right? So let's look at another one here. Our next one we'll try, what if we had the square root of, let's say, 5x minus 3 dx. Okay? Now, ultimately, we know that the square root is a power function. So if we were to rewrite it in its power form, we'd have that. True? And ultimately, that looks very similar to the one that we just did, okay, except for the power is a half instead of 4. But again, the key issue is we can't do anything with this unless it's in the form u to the 1/2. So if we substitute, if we let u equal 5x minus 3, we could certainly write that as u to the 1/2. But again, we still have this issue of having a dx there. Okay. So how do we remedy that? Well, we get the dx out of there by relating it to du. So what would du be in this case? It would be 5 dx. And so notice this time, my du and my dx are not equal to each other, but they're related. And ultimately, what do we want to get rid of? Dx. So therefore, wouldn't dx here equal 1/5 du? Agreed? Okay. Divide both sides by 5. You got dx alone, right? So that means my dx can be replaced by 1/5 du, and my new integral would be u to the 1/2 times 1/5 du. Now, what other nice property do I have at this point when I can do something with that 1/5? That ultimately would be equal to 1/5 u to the 1/2 du. And now that I have it in a pure power form, I can find the antiderivative. And the antiderivative would be u to the 3/2 divided by 3/2 Keep in mind there's a times 1/5 out here. And also divided by 3/2 is the same as times 2/3. So we'd have 1/5 times 2u to the 3/2 over 3, I mean. And so we'd ultimately have 2u to the 3/2 over 15 plus c. And with that said, our final answer is not that, because our final answer needs to be back in x. Okay? So put that up here. So it'd be 2, 5x minus 3 to the 3/2 over 15 plus c. And that right there would do it. Another thing you could do here too, depending on whether it's multiple choice or not, you could rewrite this as 3rd power square root. Write it back in radical form since it was given to you in radical form. So I guess final answer probably should be square root of 5x minus 3 all cubed over 15 plus c. One thing that you don't generally have to do is you might recognize here that if I have a 3 power and a square root, I could actually rewrite this as 5x minus 3 squared times 5x minus 3 and take a 5x minus 3 out. It's generally not expected that you bother with all that. So you can just leave it like that, even if the power is bigger than the root. Because ultimately, keep in mind that we're finding a function y here that came from this derivative. And ultimately, we want to use that function y to plug in x's to find values. True? So would it be easier to plug a value in and do the math in this capacity? Or would it be easier to have another 5x minus 3 on the outside? Wouldn't this be ultimately easier to put numbers into and find the answer? So that's essentially why we don't do it that way. All right. Questions?
Why isn't that du equals 5 dx?
Because again, u is equal to 5x minus 3.
Yeah.
So du, which is the differential u, is equal to the derivative times dx. So it's because the derivative of 5x minus 3 is 5. All right, let's do another one. Let's say we have something like cosine of 4x plus 2. So we have cosine of 4x plus 2 dx. We know ultimately how to deal with cosine in general, but it's cosine of some other argument besides x, so that means it's going to be a substitution problem likely. So let's try substitution and see if that works. We got 4x plus 2 would be the natural substitution here, because we want to get this into the form cosine u. But once again, we have cosine u dx, so that has to be remedied. So if I do that, my du then would be 4 dx, derivative of 4x squared, or 4x plus 2 that is, times dx. All right, and then from there, I'd have a quarter du would be my dx. Fair enough? All right, and so with that, I can replace my dx now with a quarter du, and I'm going to skip a step here and just write my quarter out in front. That should be done every time, true? And you can write that intermediate step if you want to, but ultimately we know that quarter is just going to end up out in front anyway. And then from there, I'm going to have a quarter times sine u, if I do the antiderivative, plus c. So my final answer would be sine of what? That would do it. Questions? All right, let me pose this problem to you. What if we had this? What if we had the same problem, but it was 4x squared? Ultimately, if we let our u equal 4x squared plus 2 dx, our du would be 8x dx, wouldn't it? True? So keeping in mind that we've already done our u substitution part with the argument, but then we'd have a dx here. Okay. What's dx equal to in this statement? Wouldn't it be 1 over 8x du equals dx? Keep in mind, why would that not be any good? We'd have cosine u 1 over 8x du. So we could certainly replace the dx with that stuff, but what did it just reintroduce into our problem? We're back to having an x in there, aren't we? Okay. In some cases, that can be remedied. In this particular case, ultimately, we could actually solve this equation for x, because this is a true equation in our sense. If we solve this for x, we could have another expression in u. Ultimately, the problem lies in, though, is once we get that other expression, which is going to involve a square root in here, okay, are we going to know the antiderivative of cosine u times the square root of something? Probably not. So ultimately, at this point, this problem right here is not something we'd probably be able to find an antiderivative for.
So we won't be given one where it's 8x.
Not on the homework. On the test, there'll be 10.
Be 10 of them?
Yeah. Yeah, it'll take you 45 minutes each to try to sort through it and then find out that it actually doesn't work. So bottom line is this substitution process, sometimes it works, sometimes it doesn't. Okay, in this case, this would be one where we would not be able to get an answer with substitution. So there'd have to be some other technique that we'd use. And in some cases, there's techniques that we can use. In some cases in this class, there will be ones that we just flat out can't do. And we may not learn it all in this class, and you might learn it in a different class. Okay. So all the ones that we do, and obviously in this section, they're going to be, substitution is going to be, it'll work. Okay. As long as you do it
Power
correctly.
of 1.
Okay. Not necessarily that, but I'll show you what I mean here in just a minute. All right, so what I want you to look at here next is we had a problem that we posed a while back here that was to find the antiderivative of tangent x. And we know that tangent x is not a known derivative, right? So therefore, we can't just simply come up with an answer for that because ultimately, we don't know an antiderivative for it. So, if that's the case, one of the techniques that we talked about yesterday is can we manipulate the integrand so that it's something that we can find an antiderivative for? And we know that the only thing tangent itself equals is cosine x over sine x. True? All right. So, if we think about this integrand now, let's think about what we might be able to substitute here, because you'll notice that if I let u equal cosine x here, what would du be? Differentiation. Negative sine x dx. True? Alright, and now watch what happens when I substitute that integral. I'm going to have a u on the bottom. True? My cosine x is equal to u. Okay. And what I'm going to have left on top? I'm going to have sine x dx. True? What do I have right here? I have almost sine x dx, don't I? In fact, if I just went negative du, wouldn't I have sine x dx exactly? So with that said, what could this sine x dx right here get replaced with? Negative du. So ultimately, I'd take the negative out in front. I'd have 1 over u here, and I'd have du here. Keep in mind, it's not u is on the bottom, so it needs to stay on the bottom. It can't just jump up to the top and be u and all of a sudden, right? So with that, wouldn't I have gotten rid of everything with x and gotten all u's in there? And also, conveniently, I have an integrand that I can antidifferentiate. Because what is... What? Because sine x dx is equal to negative du. So what do I have right here? Sine x times dx. This is sine x dx. So what did I replace sine x dx with? Negative du. Here's the du. Here's the negative. Okay. So yeah, it's ultimately just a negative 1. I just brought it out in front. You can put it in there if you want to, and then do the second step, but you don't have to. All right. So with that said, what's my antiderivative here? It's natural log of absolute value of u plus c. So final answer then is negative natural log of cosine x plus c. There's your antiderivative of tangent. Sure. It's really an antiderivative for just about anything, but whether we can find it or not is generally a different story.
So we can use that basically as a formula now for
Sure.
tangent.
So the antiderivative of tangent, sure. Or if you don't want to memorize that, you can just find it again. Okay. Now, what if, ultimately this work seems to be good. What if we didn't believe that though? What if we wanted to make sure that that was actually the antiderivative of tangent? Can we differentiate that and make sure that gives us a tangent?
Yep.
Okay. Ultimately, it's going to, with that notation, it's going to get us to sine over cosine, which is ultimately what? Tangent. Okay. If we did the chain rule there, you get 1 over cosine times the derivative of cosine. What's the derivative of cosine? Negative sine. There's your negative negative would make it back to positive, right? You'd have positive sine over cosine, which is ultimately tangent. All right. Let's take a look at one more here, and then let you know what our homework is going to be like here for today. Let's say we have something like, let's say 4x squared plus 2x plus 5, and we raise that to the 8th power. And then we know that right from the get-go this is going to be virtually impossible because the derivative here isn't going to be a constant. Okay? But what if attached to that, though, was, let's say, 4x plus 1? So that's my integrand. That's stuff to the 8th times 4x plus 1. Okay? So keep that in mind. Now remember, we always have an option here of multiplying all that crap out. It would take a while, but we could do it. So there's no reason we couldn't find an antiderivative for this. Right? It would be preferable, though, if the substitution was available, because then we wouldn't have to multiply all that out and then do the power rule for every term. You know, ultimately, think about it, we got 3 with 8 times, we're going to have a ton of terms. Right? And eventually we could get it, but it'd be a real pain in the neck to do it that way. So let's see if we can do it another way. Let's try to substitute here. So if we go 4x squared plus 2x plus 5 as our u, keep in mind that would leave us with u to the 8th times 4x plus 1 times dx. Okay. And ultimately, I keep writing this just for illustration. You don't necessarily have to write this step out each time. Okay. But it might be helpful for you to see the substitution carefully with the du part. And so ultimately, what would our du be here? 4x squared would be 8x plus 2 dx. All right, so with that said, look at what we have to get rid of. This has to go, okay? And this is what we have equal to du here. Okay, how does this compare to this?
2u.
If I factored a 2 out of that, I'd have 4x squared. I'd have 4x plus 1 times dx, wouldn't I? True. And ultimately, wouldn't this be equal to half du, if you will? Just to double check, if I multiplied by a 2 here to get rid of this half, back to du, I'd get 8x plus 2, wouldn't I? Okay. So with that said, what are we going to replace this whole thing with? It's half du. Okay. So conveniently, we end up with a half, u to the 8th du. Half goes out in front, du goes behind it. And then from there, we get u to the 9th over 9 plus c times a half out here. So with that said, we'd get 4x squared plus 2x plus 5 to the 9th all over 18 plus c. And we were able to find an antiderivative for that without having to multiply all that stuff out, which would have, like I said, been a real pain in the neck. Okay. And keep in mind, with the chain rule, could I antidifferentiate, or could I differentiate that and make sure it gets me back to what I started with? And think about how easy that's going to be. If I just do this, okay, if I think of this, keep the 1/18th out in front, if you will. This is just going to be 9 times this to the 8th. Right? The 9 and the 18 out in front are going to make a half. But ultimately, what's the derivative inside here that we'd have to multiply by? It'd be 8x plus 2. Right? 8x plus 2. Keep in mind, times a half would give us back to the what? Be back to the 4x plus 1, wouldn't it? Okay. Like I said, if you need to write that out to be convinced, feel free. But ultimately, that derivative of that would certainly get us back to the argument we started with. Okay, the next part here I want to look at here is just go ahead and go to your exercises. On your page 321, we have the work that we're doing today here is the 1 through 17 odd part. Just want to look at the directions here. It says in the first part here it says use the indicated substitution to evaluate the integral. And so they gave us what to let u equal. So from there, we'll do the work from there. And they also says confirm by differentiation. So in other words, when you get done, differentiate what you got and make sure it gets back to the integrand. Okay, so there's 2 parts to that. The second part, you're using substitution, but they did not give you the substitution. You got to decide what to let your u be. See if you can come up with an answer for it. So that's the 1 through 17 odd part. And then the once we get to the 31 part, actually we're not going up to 31, are we? We're just going to 27, right? Yeah, just 18 to 27. All right, well, I guess that's it. Those are the only 2 directions then. The first part, they actually give you what to let u equal to, and the second part, you need to decide what to let u equal to. Okay? All right, so we'll